Thank you for coming to the session. Welcome to this technical session. I suppose the first thing I should say to sort of get us started off in the right direction is to tell you that perhaps in some ways this presentation is kind of flying under a false flag a little bit. And that's because you read that title and it would be a reasonable interpretation for you to think, well, what Mike's going to be showing me is how I can start using object-oriented programming language. Start using object-oriented programming in my LabVIEW work. And the problem that I have with that interpretation is that little word "start." Is that what you're going to learn today is not how to start using objects, or not start how to use object concepts. Because if you've been paying attention, you started using objects the moment you booted up LabVIEW. Because LabVIEW is from the time of its inception in 1986, it was built on an object-oriented foundation, and it continues to have that foundation under it. So regardless of whether or not you think you're using object orientation, you are. Okay? It's sort of like parallel programming. I mean, how many of you have programmed applications in LabVIEW that you have parallel processes running? Everybody hold your hand up. Right? Okay? That's because it's inherent in the language. In fact, it would be very, very hard, it would be very, very difficult to create an application in LabVIEW, a non-trivial application in LabVIEw that was not parallel. Or in this case, would also not use objects in some way or another. What I am going to show you is a way of, how to leverage some of that object-oriented underpinnings to allow you to create classes of your own, to do things that you want to do, that help simplify the processes that you're trying to build. That in doing that, the first thing we need to do is we need to have some kind of a glossary, so we can so that when we're all talking about things, we're all talking about the same things. And this is important because, unfortunately, a lot of people, when they get interested in object-oriented programming, the first thing that they do is they run down to Barnes & Nobles or a bookstore somewhere, and they buy a book on object-oriented programming, which tells you all about object-oriented programming in C++, or in C#, or in Java. Now, what's the obvious problem? We're not C++ programmers. We're not Java programmers. We're LabVIEW programmers. All right? And so, while we're going to use a lot of the same words, there will be a little bit different usage to them. All right. So the first thing we're going to look at is the term class, and it's an abstract data type. Now, if that sounds a lot like the definition of a cluster, you're right. It is. And in fact, the way that classes are implemented in LabVIEW, classes basically are just really fancy clusters. Okay? Next is the idea of an object. An object is an instance of a class. Okay, now, what that means is that in the LabVIEW world, object equals wire. Okay? An object, a LabVIEW object, a LabVIEW class, is not some sort of strange thing that is like totally outside the realm of what you're used to seeing. Objects are wires, which means we're still in a data flow environment here, folks. We're not leaving the data flow that we're all used to working with. Next, we have property. Property is a piece of information that tells you something about or describes an object. Okay? Then finally, you have a method. And methods are functions associated with a particular class that can make it do something useful. Now, what does something useful mean? Well, it depends on what the class is for. If the point of the class is to create something on your user interface, you might have methods to draw objects on the front panel. If the point of your class is to save your configuration data or retrieve configuration data from a database, you would have methods for retrieving whatever the particular pieces of information are that you're wanting to get out of the database. So this is sort of, these four terms here sort of define the arena that we're going to be playing in. And just to recap real quickly, a class is a particular kind of wire. An object is a particular wire. A property is information that is being carried on that wire that tells you something about that particular object. And then a method is something that is a function that uses data from the class data and data that you feed into it externally to do something that you want done. Now, some of the key features of object-oriented programming that we need to look at. First of all, there's what's called here dynamic dispatch. Now, dynamic dispatch is probably the one thing that most people get confused over with object-oriented programming. Basically, object-oriented programming is just like polymorphism, or it's very similar to polymorphism. It's a form of polymorphism. Now, if you've ever, in your normal, quote-unquote, normal LabVIEW work, if you've ever taken, the add function and wired an array of numbers up to one side and a scalar number up to the other side, and you got an array out, guess what? You just use polymorphism. What polymorphism does is it looks at whatever the inputs are, and it automatically adjusts itself to be able to deal with those particular data types. Okay? Now, the thing is that if you're developing a polymorphic VI, notice that you have a very different view of the process. All that flexibility doesn't happen by accident. It doesn't happen by itself. If you're developing a polymorphic VI, you have to create all the individual instance VIs to handle the data types that you want to be able to handle in your polymorphic VI. Okay? And dynamic dispatch is very much the same kind of thing. The primary distinction between dynamic dispatch and polymorphism, there's really two things. Number one, the biggest difference is when the polymorphic or when the dynamic dispatch VI decides which instance is going to run. In other words, with a normal polymorphic VI, as soon as you wire up an array of U32s to that add function, LabVIEW decides, all right, I got an array of U32s. That tells me that that's the first piece of information I need to know which specific adder I need to call under the covers to do this add. All right? Well, now, dynamic dispatch does not work that way. The thing is that dynamic dispatch, the data types are dynamic. Okay? So what happens is that instead of making the decision at compile time, when LabVIEW is actually compiling your code, a dynamic dispatch VI doesn't decide until you're actually running it which of the specific instances or which of the specific methods is going to call. Okay? Now, to do that, obviously, you have to have a different kind of wire, right? Because in LabVIEW, wires are, unless you use the evil purple dynamic dispatch wires, or dynamic data type wires. You can have string, you can have numbers, you can have arrays, you can have references, you can have paths, but once you drop that number down, it never becomes anything else. Numbers can't magically become strings. Strings can't magically become paths. Right? All right. So for dynamic dispatch to work, you need a different kind of wire. And the class wire in LabVIEW is different in that it can have a sort of a high-level type, but then the specific information of what is actually being carried on that wire doesn't get defined until later. And we'll talk about how all of that works in a bit. Next thing we need to talk about is inheritance. Inheritance is a wonderful thing. What inheritance does is, if you have, we sort of touched on a little bit here, but if you have this hierarchical structure, you have classes, you have subclasses, and you have subclasses, and so on. What inheritance does is allows the lower, child and grandchild classes to use and access both the data and the functionality that was defined in their parent classes. Okay? So if a parent class knows how to do something, and the child class is going to do it the exact same way, your code is done. You just let the parent class will do it for you. Okay? Now, if you think through this carefully, this inheritance will be a major win for you. If, however, you don't think through it carefully and clearly and make notes about what you're doing and really think about the process, then inheritance can create a massive can of worms, and life will not be good. Okay? Which brings us to our next point, which is organization. Now, organization is not necessarily, an aspect of object-oriented programming, but it is critical. Every application that I've ever seen was written with object-oriented, structure that was a real train wreck. That was horrible. It was too large. It was unreliable. It crashed. Every one of them. You could trace it back, and you see that the root problem was a lack of organization. The developer basically got partway through it and he got confused as to what this meant or what that meant, and so he ended up inadvertently calling the wrong things, doing the wrong things. What I like to say is that a developer who is undisciplined can kind of get by in normal LabVIEW. But as soon as you start using explicitly defined classes, if you aren't organized, if you're not careful, if you're not structured in your thinking and the way you approach your work, you are lost. Oh, and by the way, one of the things I'm going to talk about here, the two major pieces of organization that will help a lot and keep you out of trouble are naming conventions and file name conventions and directory structure conventions. And if you want to scan this QR code, on my blog I did a post called Conventional Wisdom, where I talk about all the various different kinds of conventions that you can implement. And by the way, conventions are a really good thing. And largely, it doesn't really matter what your convention is, as long as you always do it the same way. Where you will get into trouble is where you do it one way in one place, and another way in another place, and another way in another place. Because sooner or later you're going to come back to the first system, and you will have forgotten how you were doing it. Is it? Oh, okay. So, okay, now, one of the things I like to do as I'm naming my classes is I like to mirror the structure of the class names with the structure of with the directory structure that those classes are stored in. Okay, for example, here would be the name of a class. GUI update underscore digital underscore unsigned word LV class. Okay? So you're updating something in the GUI, a digital control, an unsigned word digital control. Okay? Now, what I do is when I go to save that software, now you go to save that class, and I go to save, in this case, the sub-VIs that are associated with it. See, I've got GUI update /digital / unsigned word, slash, and then sub-VIs. So you follow a convention like this, even if it's something this simple, it will save you lots and lots of time. Because what happens is you're saying, well, I've got this sub-VI for this class. Now, where did I save it? Well, you don't have to worry about where you saved it anymore, right? Because if you know what the name of the class is, you know what the path is to get to it. You know where it's stored on disk. Okay, now, so now we're going to start getting down some of the specifics. And the first thing that I like to do, well, first of all, we're going to talk about an application where we're going to posit a sort of like a little test application. Then it acquires some data, controls a couple of things, and it already exists. We already have it running. It already is doing exactly what it's supposed to do. The thing is that it pulls in its configuration data, which basically there's 3 pieces of configuration data that it uses. But right now it's pulling those in from an INI file. And let's say that being smart developers, you decide that pulling the configuration data from an INI file is not a good thing to do because it's not secure. It can be manipulated. It can be changed. All sorts of nasty things can happen to it. And so you want to put it into a database. Well, that's what we're going to do, is we're going to look at the structure that we need to create to be able to make that conversion from a text-based storage of your configuration data into a database-based storage of your configuration data. Now, you might think that this is going to be a really major change. Well, guess what? It's not. Remember, the primary reason you go through the design process the way you're supposed to, the way you think, the reason you think things through, the reason you come up with an organized structure to your application is so that when things like this happen, you can do it. Like for instance, in this application, because the interface between the data storage and the rest of the application is very clearly defined, I know I've got exactly 3 things I got to change in terms of my original code. I don't have to go hunting through 45 different places. I had an application one time where the original developer read a configuration string out of a text file, put it into a global variable, and then passed it around the application. Now, what was actually in that string that he read out of that file was a tab-delimited list of parameters. And everywhere that string was used, it was parsed over and over and over again. And nothing was labeled. Nothing had any enumerations. So you just had to remember, oh yeah, see, item 3 in the list, that was the sample rate. What was that item 4? See what I'm saying? Bad design. So if you're going to change any one of those parameters, you would have to have gone to every place in the code where that string was parsed. And by the way, that parsing wasn't done in the sub-VI. Really good stuff. All right. So if you are smart in your design, if you're smart in your work, you save yourself lots and lots of time. I always tell people that one of the guiding principles I have is be as lazy as possible. I don't want to have to go back and redo code 5 times. Once is enough. I can go on and do other things then. Okay? So first we need to create a blueprint, which, as I said, is to define all those contact points between what the contact points are going to be between the class that you're going to be creating and the application. Next, we need to design the structure. Now, in other words, what classes are we going to need? Okay, well in this case, we are, as I said, we're going to be calling some configuration data. And so we can say, let's have a top-level class we'll call config data. And because there are 2 basic places we can get data from, either a text file or a database, we'll have 2 subclasses. one called text and one called database. I like to be as obscure as possible here. All right? That was sarcasm. But in any case. So, now we're not really interested in text at this point, but let's look at in terms of databases. Now, how can you talk? One of the things you can look at is, all right, how do you talk to databases? Well, the primary way you talk to a database is ADO, something called ActiveX Data Objects. Works really great. And you can have, there are ADO drivers available for almost every database on the planet. However, almost every is not the same as all. There is one rather notable exception, and that is a little database called SQLite. It's really popular. It's a neat little database, and it will run on about any platform you have. It'll even run on some real-time platforms. Okay? The problem is because it's so lightweight, it doesn't use ADO. It has its own custom little DLL that you have to call directly. All right? So here we have two fundamentally different ways of talking to the database. So let's have two subclasses under the database, one for SQLite and one for ADO. Okay? But now what about ADO? Does that need to be broken down anywhere? Well, again, ADO does a pretty good job. That and SQL standards does a pretty good job of hiding which specific database you're talking to. But there are differences. For example, ADO, most databases like Oracle, SQL Server, most of your large systems, the way you access them, well, first of all, they go to actually incredible lengths to hide from you where the data is actually being stored. And they do it for a really good reason, because if you don't know where it's at, you can't break it. Right? All right. Now, on the other hand, got a little database here called JET, which is actually what everybody thinks of when they talk about a Microsoft Access database. First of all, Microsoft Access is not a database. Microsoft Access is an application development environment that allows you to build programs that utilize a database. Now, the one it uses by default is built into Windows. It's called JET. Okay? If you have a Windows machine, you've got JET available on your computer. Likewise, something a lot of people don't know is if on your LabVIEW development system, if you have right now the data supervisory control toolkit, you have an instance of SQL Server running on your computer. You may not know it, but you do, and you can use it. Likewise, if you install, say, the demo version of that toolkit to try it out, and you uninstalled it, SQL Server is still there, because LabVIEW because the uninstaller doesn't uninstall that. Okay. So in any case, under ADO, we can define one subclass for JET, because it is going to require a different way of communicating, of specifying what the connection is, because it requires a path to a specific file. Whereas with other ADO systems, no. So right now we'll put one for JET, and we'll sort of hold it out, because in the future we may have others. We may need others. Now, so getting down to specifics again. So the first thing we have to do in terms of actually taking that little block diagram, that little chart, and turning it into something actually useful, is sort of like doing the rough framing. And when you're building a house, I mean, the first thing that they do after they pour the foundation is you get a bunch of carpenters out and they do what's called the rough framing. And that's where they put up sort of the walls, and they probably, will put plywood on the outside just to close it in so the rain doesn't get in. And so that's basically a structure, the raw structure that later people will come in and will finish out. And so that's where we've got to start with here, is sort of our rough framing. And in the case of what we're doing here, we have our rough framing is creating the classes that we're going to use. And the information to do this, I pulled directly off of the off that table we created before. Okay? So I created the classes, I created the directories for them to reside in. I used my naming convention here. So the top level class is called config data. So we have config data underscore database underscore ADO. Okay. So this basically sort of sets up the structure. Does nothing else. Okay. Likewise, down here, I create some virtual directories that I'm going to need, that I know that I'm going to need to use, and I'm going to put things in. And likewise, and finally, I take this whole structure here, and you'll notice, what did I put it in? I stick it inside of LVLib, a library. Why? Because libraries allow you very closely defined access, your access rights. And you'll notice that every one of these little icons here has a key on it, which is either a yellow key or a red key, meaning that the contents of those items are either private or they're protected, which means anything outside that class can't see them. There is one exception though. Interface. That is the folder where I put the VIs that I build that are going to form the interface to this class, for this class, to the rest of the outside world. Again, if you control access so you can't go behind one of the higher level classes backs and directly call a subclass, which you don't ever want to do, life gets better. It gets simpler. It gets easier. Okay. Now, once we got that basic structure, now we can start filling in some of the infrastructure. And in terms of infrastructure, what that means is we need to start adding in some of the code for managing the data. However, I don't mean the application's data. What I'm talking about is the data that this class structure is going to need to manage its own operation. Okay? And if you think about it, the various different classes that we have, there are basic pieces of information that are going to be needed at each level in that hierarchy. For instance, at the top level, at the configuration data class level, there are two pieces of information that I can think that you might going to need, regardless of what subclass you actually end up talking to. Operator ID and a password. You might need to log into a database. You might want to validate that the operator really is authorized to do what they're trying to do. Okay, so that information is going to be needed by any subclass. At least some of that data will probably be needed by any of the subclasses. Okay, so it needs to reside in that top level class. But therein lies the problem. Remember what I said objects were. Objects are wires. Right. And LabVIEW wires are not what? They are not global. In other words, if you want to know what's on a wire, you have to connect to it, right? So, how do we handle this? How do we deal with the situation where we want to have some data that's going to be global, that's going to be available to all of the subclasses, regardless. But yet, we just can't pass wires because we don't have contiguous wires. Well, there's a really good way of doing it, and the idea is it's very simple: is to have some sort of data storage that we can put our data into, and then we just pass the reference to that data around. And as it turns out, LabVIEW's got a really, really good resource for doing that. It's called a DVR, a data value reference. So to create one of these things, first thing I do is I create a type-defined cluster with my two pieces of information, my user ID and my password. And then I create this VI here to initialize my data value reference. Now, notice three things about this. First of all, you notice the overall structure of this is basically the same as a functional global, right? Which means that, whether or not this case here runs depends upon whether or not this reference here is valid or not, or invalid actually. If it's invalid, then we run the initialization code, which initializes the shift register. So every time after that, you will always get a reference to the same DVR. That's point number one. Point number two, look what my data type is for the DVR. It's my cluster here. Well, what does that little black quarter tell you? It's a type def. Anytime you're defining a DVR, anytime you're defining a user-defined event, queues, notifiers, whatever, always, always, always use type definitions. Okay? Now, the reason for that is real simple. Is that if you probe that wire and ask to find out what the data type of this wire is, LabVIEW will say that this wire is a reference to a DVR of that type definition. If that value was not a type def, if that cluster was not a type def, you could probe this wire and it would say it is a DVR of a cluster with two elements, both of which are strings. Now the difference is subtle, except for this, is that if you then change the cluster, it'll break all your references. Because as far as LabVIEW is concerned, the data type of this DVR reference has changed. But if this is a type definition, you can change this as much as you want. And this never breaks. Okay? This is why a lot of times, if I'm working on something new, you drop bearing down inside my code, you'll see a DVR set up like this, and it will have a single Boolean control that is type def. It's like, well, why in the world is my type def a Boolean constant? Because I wasn't sure that's what I was always going to need. And if it turns out that was all I needed, no harm, no foul. Not a problem. But if it turns out that at some point I find out that, conditions of the Boolean, I also need a string and a number and all that. Now I can go and I can modify the type definition, and everything else just falls into place. Okay, now, in terms of how you get data in and out of our thing, this is I created these two guys here. This is for reading the user ID value. This is for writing the user ID value. Okay. Now, you also need, before we created the DVR, that other VI we looked at, that was what was in here. But now we need to take that DVR reference, and I take that DVR reference, I make it the class data for my parent class. And then I write this little bit of code here so that when this runs, it looks at the configuration data coming in, and if the DVR value hasn't been initialized yet, it calls this and initializes it. If it's already valid, it selects the other case, which does nothing, just passes the cluster or the class wires through unmodified. So this will automatically modify or automatically initialize your parent class. Okay, now after I do the parent class, and then I start looking at the children classes, at all the subclasses, and I say, all right, do these subclasses, do they have global data or do they have data that I'm going to want to make globally available to all of their children? And if there are, I take this process and I just repeat this process, except in that subclass. Okay. And then when it gets down to the initialization part, this is what the initialization code would look like. In this case, it's the database subclass. And this all, from here to over that way, that all looks familiar, right? We saw that before. Question is, what's this little funny icon here? Well, one of the things that they realized very early on when they were coming up with the ideas of object-oriented programming was that sooner or later you're going to have a child that's going to want to do exactly what the parent did, but a little bit more. Okay? And so what this funny representation here does is this is saying is when this child class runs, the first thing it's going to do is it's going to call and run the parent. So the parent's initialization code, the parent version of initializing new runs, and then so the parent cluster or the parent DVR is initialized, and then the child its version also runs so that it gets initialized. And by the way, you can go this down multiple levels, so that when we'll talk about it in a second. Now, so once we have this sort of structure set up, how do we actually go about creating the objects? Creating the object that we're going to use. And here's a function that I've used. You can create one programmatically like this. You can also do it like you would with any other LabVIEW data type. You could drop down a constant, wire up to it, and you're on your way. Okay. The problem is that if you do that, you could end up where you have all this. See, the thing is, when LabVIEW loads a class in, it also loads into memory all the VIs that are associated with that class. Okay? Which means you could end up with a situation where a whole bunch of stuff is getting loaded into memory that you don't need and that you're never going to run. Okay? So the solution here is to load your classes dynamically. And that's what this code here does. And basically what it does is here's an instance of the parent class. This function here returns the path to the parent class. And because I've been using my naming and directory structure conventions, if I know where the parent class is, I can find any of the children classes because I'm using the same convention throughout. So I get the parent class. I strip off the name of the class itself. So all I have here is the directory. This function here goes out to my INI file and looks up what I've said, what class I want to create. Which in our case is, do I want to use text, INI, or do I want to use jet? Well, this case I want to use jet, so it'll return the data associated with that. Now, why did I store that information in the INI file? Well, think about it. Can a program go out to a database that it doesn't know exists to find out whether or not it should use the database? Right? You got it. That some basic piece of information has to be in some place that you know is always going to be there. And in Windows, you got exactly two choices. You got an INI file, and you got the Windows registry. Of the two, the INI file is a lot safer. Because at least ways, then you don't have you don't run the danger of one of your users getting in there with regedit and going crazy and trashing their whole computer, right? I mean, if it's in the IFL, the amount of damage that they can do is really limited. So I store this in the II file. So I put together a path. I have a path, completed path to the child class here. This function here opens this class, creates it, creates that child class. But you notice this funny sort of purple wire here? In LabVIEW, every class that you create is, you follow up the hierarchy far enough, is a child of a class called LabVIEW object. And that's what a LabVIEW object class wire looks like. Okay? So what I do is I've got my class, I cast it to be, to be the parent class. Here's our initialized new. So when that gets called, because what it really is on the inside is whatever the child class is. It's the child class's method VI will get called, and the first thing that child class's method VI does is what? He calls its parent. So the child gets initialized, and the child gets initialized, and by the time you come out here, this object is fully initialized, ready to go. Yes, sir?
But you cast it to the parent class.
Yes.
How does it know that it's really the child?
Because it's what it is internally. See, if you, what actually will happen is if you at runtime, if you probe this, what the probe will tell you is, it'll say it is, the class is config data.lbclas. All right. Then down below it'll say, but the actual class is, and then we'll get the name of the child class. Okay. What happens here is LabVIEW can hold on internally. They say, all right, this is really the child class, but we'll let it masquerade, so to speak, as the parent, so you don't break any wires. So you take this reference, you take this guy right here, that wire, run it to another dynamic dispatch, and it will always call the dynamic dispatch VI for that child class, unless that child class doesn't have one. And then we'll call the next nearest parent one. Now, then, okay, so we have all of that done. And so we have initialized all of our functions. All of that we have left to do now is we need to finish out building out the remaining methods, which means implementing those methods that actually get the 3 pieces of information that we need from the database, right? Which means, in terms of this presentation, we're just about done. Now, why do I say that? Because we've already been through everything that you need to do. Object-oriented programming is a very iterative process. You learn 4 or 5 basic things, how to do 4 or 5 basic things, and you'll find yourself doing those same things over and over and over again. Okay? For example, as I said, to finish up, you just repeat the preceding steps as necessary. Okay? First, you create the parent method. And you give it whatever it needs to have on the front panel to do what it's supposed to do. Well, you update the parent icon, the connector pane, the front panel I/O, whatever needs to have, whatever is needed for that particular method. Then on the parent block diagram, you put whatever code you want to have executed by default. In other words, every child does not have to override every method, right? Every parent method. So one thing you can do to save yourself a lot of hassle is if you're a child class needs to do the exact same the parent did, don't overwrite it. Just let the parent method handle it. Okay? Then you store the finished parent in the interface and subdirectory. Because remember, that's the one that is publicly accessible. And then for each subclass that needs to override the parent, create is say you override VI, and then modify the child's block diagram to do what it needs to do. Okay. And that's about it. After this, it's all about practice. As I said, it's all about learning to think logically about what it is you're trying to do. Think, be very ordered, be very structured in your thinking about things. Because the more ordered, the more structured, the more organized you can be, the easier it will work. And by the way, don't be afraid to rework things. You might get remember that every development project is also a learning process. Not only are you creating the application that your customer needs, but you're also learning what it is that your customer needs. And so if you get partway into this process and you realize, geez, that's so much easier if I just move this piece of data from here to here, and then I can have my dynamic dispatch work in a little bit different way like this, do it. You don't want to be in a situation where you are constantly living, where you're constantly living with working around decisions that you made that are no longer valid, and you know are no longer valid. You'll spend more time worrying about it, fixing bugs related to that, than if you just fixed it. Okay? So, the final little QR code here is the one from my blog, notattainline.com. Feel free to drop by and check. I try to talk about, write about very concrete sorts of stuff, the things that that people will run into. So, questions, please? Sorry.
What's the rationale for using dynamic DVRs as opposed to just putting a cluster up in the parent?
Well, the thing is if you have a cluster, that cluster will only be available in that one object. Okay.
It'll be available.
Yes, but see, the problem is that every child has a parent, right? Every child is also an only child. Okay? What happens if you want to have two child objects that are siblings, that don't have a parent that is of the same class, but are the same parent? In other words, they share the exact same data.
Yeah.
Okay? The only way to do that is because you have separate wires, because objects are wired, right? The data on wires is not global. So you have to come up with some way of sharing a reference so that they can get to the global data. That's smart.
The answer to the question is that because objects in LabVIEW are by value, not by reference, every time you branch the wire, you're effectively cloning the object. So unlike the real world where I may have a can, in LabVIEw, if I branch the wire, now I have two cans. If I branch again, I'll have 3 or 4 or 5 cans. And the only way to keep that data shared is your reference.
Yeah. Okay. For example, does anybody else here have a father who's named Larry? No? Oh, okay. How about a mother named Lorraine? Oh, okay. The point I'm trying to make is if there was somebody else here that has a father named Larry, that doesn't mean we're brothers. Right? And so conceptually, that's the exact same situation you have.
DVR, they're like pointers.
Yeah, very, very similar, except the advantage of a DVR reference is that it's structured. In other words, you remember the heartbleed thing? The thing that was at the basis of the heartbleed bug from a year or so ago, where and all the internet is unsecured, and it's all, end of civilization as we know it. Well, the whole problem with that was in C, there's a low-level function called malloc. And basically, what it does is you give it a number, and it will give you back a pointer to a chunk of memory that size. No error checking. Okay? So, what the heartbleed bug did, in essence, is it got a reference, and then instead of reading the 5 or 6 bytes or whatever that it said, that the thing, it got a pointer, it just started reading. And sometimes it would find good stuff. Sometimes it would find passwords in parts of the memory that were supposed to be secured, but weren't. Okay, now, the reason I bring that up is because when you have a DVR, the DVR is not just a dumb pointer. It actually says this is a pointer to this particular kind of data structure. So you can't read past the end of it. You can't read something different than that. If you define it as a DVR containing a cluster with two strings in it, that's all you can put into it. That's all you can get out of it. You can't read past the end of it. Okay? So in a sense, yes, it is very much like a pointer. You would use it logically like you would a pointer. Okay?
It's tight.
But it's tight. It's secured. Okay. Other questions? Yes, sir.
Does that mean that for any class that is going to have children, its data that it would share with its children should be in the DVR? But if it's
if the data is going to, if you want the data to be global, in other words, if you have a parent class and you want all of the instances of the child classes to all have access to the same value, yes, that needs to be in a DVR. If, on the other hand, the structure you're building says, well, that it's okay for this child to have different data than this child, that can be real useful at times. So in that case, then yeah, you just take your data values, put that into the class data, and you're good.
And obviously, if you have a child class that doesn't have children, then its private data could be a cluster or anything.
Yeah.
Gotcha.
Not necessarily. Because if you think about it, every time the wire branches, so if your child class is going to have one wire continuously from end to end, you don't have to worry about it being in any data value reference or the cluster itself. If that wire branches, you now have copies of it. And if whatever you change in there has to be shared, then its values must be data value as well. Think of a light bulb. You have a child class's light bulb, and you want its state to be on or off. You only really have one light bulb out in the world, and you branch that wire and set one on and one off. You have two states for one on.
Yeah. That's a philosophical, it's also known as Heidegger's light bulb.
Yeah.
How many LabVIEW programmers does it take to train?
Yeah.
It depends on whether it's the DVR.
Yes, sir.
So I've never used the classes or this type of object-oriented programming.
Yes.
So I don't really know how to decide whether I need to use this or should try to use this or not. Is there some kind of a basic idea why we're going to use this and how to decide?
All right. The places where I've used it, sort of as a, to get started. Actually, this was one here. Was for accessing the configuration data, and it's and because of because of the way I sort of write code and whatnot. I mean, it's sort of like a self-contained little box. It's like a well-defined little subsystem. And one of the things I would do is I would recommend what basically NI's object-oriented programming class recommends, which is find some little chunk of your code that's a clearly defined subsystem, and try making it object-oriented. Experiment with it, play with it, see what because and the thing is if it doesn't work for you, that's fine. Some people's brains don't work that way. All right? And if yours doesn't work that way, that's perfectly fine. It doesn't have to. Regardless of what everybody else says. By the way, in case you're wondering, object-oriented is dying. Seriously. A year or two ago, the guy who was responsible for establishing the undergraduate computer science curriculum at Carnegie Mellon University came out publicly and stated Carnegie Mellon will no longer be teaching object-oriented programming concepts to undergrad students. That comes as close to a death knell. And there are other things coming like functional programming and imperative programming, really neat stuff. But the thing is that if your brain doesn't work that way, fine, don't use it. Work with whatever works for you. I often tell people that the sign of good code is code that when you read it, you can tell what it was supposed to do. Right? The sign of exceptional code is code that when you read it, you can tell what the developer was thinking. And there are ways of doing that. So whatever is that give it a try. Some little piece like this, like a database, interface to configuration data works is a good application. So what's called would formerly be called like a hardware abstraction layer, where say you have a test system that you have say a particular instrument that is in, but some of your systems use this instrument, and some of your systems use another instrument, and some of them use another third instrument. Right. Wrap that variability in what's called hardware abstraction layer, so that from the outside, the calling application just sees a call to a VI that's going to run, that's going to say take a particular measurement, return a particular voltage, pressure, whatever. Inside, use the object-oriented to pick which class, which subclass, which defines which instrument you're going to talk to. Okay? So start with a small piece like that, and as you work with it, you'll learn. Like, I can see, you'll be able to understand, where it's going to work best in the way you develop code. See, I can tell you all the places I use it, and it might not, be of any value to you because I may not write code the exact same way you do. My brain might not work exactly the same way it probably does. My wife would say, your brain doesn't work the same as anybody's. But the point is that, see where it fits into the way you develop code, the way you write code. And you might come up with something really, really good that you want to share with everybody else that nobody else has thought of. That's great. And it's certainly possible. Mm-hmm.
Are these slides available on your blog?
I'm sorry, what?
Are the slides available on your website?
They will be.
Okay.
In addition to which, if you want a more detailed example of this, there was a series of three posts. It was called Objectifying LabVIEW and Objectifying the Test Bed, and I forget what the name of the third one was. On my website, on my blog, yes. And basically, a lot of this material was derived out of those three posts, and it was just, so that would have a lot of the detail that I don't have time to get into here. Anything else? Okay, well, looks like we're good then. Thank you very much for attending.